Okay, hello everyone. It's my great honor to introduce our speaker today. Dr. Vincent Böning is a postdoc at Max Planck Institute for Solar System Research in Göttingen, Germany. He got his PhD at the University of Freiburg, Germany, and Leibniz Institute for Solar Physics. He then worked in the Solar and Stellar Interiors Department at MPS. He is currently a member of the Planetary Interiors Group of the Planetary Science Department. Dr. Böning studies heliosismology and hydrodynamic simulations of planetary interiors. His research interests include turbulent flows like solar and planetary interior convections, emergence of large-scale flows like differential rotation, planetary jets, and meridional flows. He is also interested in large-scale features like solar supergranulations and Saturn's polar hexagon. Let's thank to our speaker again. And Vincent, you can start your seminar.
Thank you very much, Ruiju, for the invitation. And it's a pleasure to be here and see many of you again after such a long time in COVID exile. Let's see, so I'll share my screen. Yes, I've prepared a talk. It's, I think, two more or less equal parts about solar supergranulation and the convective conundrum. Whoops, I have to do something. I have to make it run. Yes, so do you see my presentation?
Yes, your
good.
Beautiful title.
I just have to get rid of this control panel thing. Okay, here we go. So, yes. Yes, so to start off with a short motivation for studying solar interior convection. Understanding convection is important for several reasons. One, maybe very obvious one, is that convection transports thermal energy outwards from the solar bottom of the convection zone up to the solar surface. And maybe even more interestingly for us here is that convection transports and potentially even amplifies magnetic field. It could, for example, play a role in active region emergence, as shown on the top right plot here, where several active regions were averaged, and the emergence location is this white dot. So I can maybe make a pointer here, laser pointer. Do you see pointer? Yes, very nice. So at the white dot is the average location of emergence, and statistically there's a inflow into this location a bit from the retrograde direction a few hours before emergence. Not only that, convection can act as a turbulent diffusion. It can produce magnetic fields also via the alpha effect. And also convection plays an important role in helping to maintain the differential rotation and also the meridional circulation. And of course, the differential rotation is important for producing shears in the magnetic field in the omega effect of the solar dynamo. And convection happens on several scales on the sun, as you probably all know. So the smallest one is solar granulation, which has typical scales of 1 megameter of 20 minutes and of about 1,000 and likely also more meter per second velocity. And observations on the left have been pretty well reproduced by numerical simulations on the right, which are not to scale. And so we think we mostly know how granulation is working. But for solar supergranulation, this is not the case. I think it's fair to say. So supergranulation is a bit bigger. It has scales of about 30 megameter in spatial scale, time scales of about 1 to 2 days, and typical velocities of 200 or 300 meter per second. And quite related to this is the so-called convective conundrum. And I'll explain you very briefly now and much more in detail in the next slides what this is about. Very briefly speaking, so this is an updated plot from a paper from Guizot and Birch, 2012. Very briefly speaking, the flows measured in observations, which are the black and red curves, are quite different to the flows from simulations, which is the gray curve shown in this plot here. The flows are different, larger at large scales in the simulations by at least an order of magnitude in flow, so at least 2 orders of magnitude in the kinetic energy. especially at large scales, which are larger than supergranular scale, which is here at L of about 120. So L is harmonic degree or angular degree, which comes from the spherical harmonic transform. I expect that you all know this. If not, just ask and I'll quickly explain. And so the convective conundrum, it's a riddle. So the question could be asked in different ways, what this is about. One question could be, how do supergranules and the supergranular peak in the spectrum emerge? So this peak here, why is there a peak, and which is not present in the simulations? Why do large-scale flows have such a small amplitude in the sun? That's this part of the curve compared to simulations. How do supergranules emerge? Just not looking at the spectra, but looking spatially, you can see the supergranules already on a simple Dopplergram. Why are they there? And another question could be why observations and simulations are different, especially at large scales. And a related question could be, but I will not touch it in this talk, how convection generates solar-like differential rotation and not anti-solar-like differential rotation. So we'll now have to look a little bit closer into this plot of the kinetic energy as a function of harmonic degree, because a few things have happened in the meantime. And not only that, I was not showing one result, and that's the result of Greer et al. In the last plot, but I should show it also now. And the original curve is the one that is shown up here. So this result was obtained with ring diagram analysis as opposed to time distance for the curve of Hanasoga et al. Down here. And as you can see, these are, again, also quite different and apart by a few orders of magnitude. And the Greer result, it is more or less consistent with the simulations, let's say. And so there's a difference in Healy's cosmological results and also the potential difference to simulations. And quite a few people at MPS have worked on this topic in the last few years. And the first thing I think that happened is that Aaron Birch found out that there were several inconsistencies just in the definitions of the spectra. And one, for example, was that different of the publications, they use different definitions of spherical harmonics. For example, different of a factor of 4 pi, which already is a factor of over 10, so an order of magnitude. And also some of the curves that were plotted summed the energy over the different azimuthal orders m, and some did not. So some plotted the energy per multiplet, so to say, and one per mode. And this is a factor of 2L plus 1, which is a pretty big factor. And I think it doesn't matter so much which definition one uses, as long as one uses a consistent one among the data plotted. And what Aaron did, looked at all these definitions and took then the correction for the original curves, which were plotted in gray, was black and red curves. So you can see that some of the differences were alleviated, but not so that the overall order of magnitude discrepancy between the ring diagram and the time distance results vanished, and not also the simulation curve. Also, it stayed more or less where it was. Then Kaori and me looked at the two, Kaori Nagashima and me, we looked at the ring diagram and time distance methods that were used for making the two plots in the earlier slide. Kaori looked at the Greer et al. Work of 2015, and she found a few things that should be improved in the ring fitting code. I will not go into details because it's quite technical, I think. And I'm not so much an expert on ring diagram analysis, that's the other reason. And she found some differences that would appear, but these differences were not an order of magnitude, but they were less than that. So this is not, that was her result, not enough to describe the discrepancy between the ring diagram and time distance results. And what I did, more or less in parallel, a bit later maybe, I tried to understand the method of Hanasoga et al. And I used synthetic flow fields from Muram, from the hydrodynamic simulation, actually including also magnetic fields. And so which is, for small scales, for the granulation scale, similar to the sun, but for the large scales, it's a little bit different from the sun. Also, it has two large amplitude. So the results for the true sun might be different. So I used the simulated sun to check the method basically. And I produced the method by Hanasoga et al. Basically with a forward model and a statistical model for the errors and so on. And I found that the method roughly works, but the estimate of Hanasoga et al. Would be, in the case of Muram type flows, too low by a factor of about 2. And converting to energy, it's again a factor of 4. So there's some correction to be applied. And this can be seen, this is summarized in the plot I'm showing on the right here. So basically, the true flows are the green, shown by the green line. And the estimate that would have been given by the original method of Hanasoga et al. Would be the blue curve. And basically, if I correct the method and so on, I get in 2 different ways. I get the two orange curves, which are supposed to be upper limits, and which are in this case actual upper limits on the flow amplitude. And at the largest scales, you can see the factor between Hanasoga et al. And the true flows is about a factor of 2. I found a few additional things to keep in mind. Is one thing I found is that the signal to noise ratio in the data depends on harmonic degree, which was assumed constant by Hanasoga et al. And I also found that the deep focusing geometry is not so well focused in the target depth, but the method is mostly sensitive to surface flows. And this I will illustrate in the next slide. But before that, a quick intro how Hilly seismology works so that this can be better understood. So to wrap up in just one slide, first one takes observations. So HMI programs, for example, one extracts an observable from it. It could be a mode frequency or a travel time or a ring shift. And then one makes a forward model for this observation. Could be from eigenmodes, could be from a model of wave propagation like ray path. This is usually a linear model and includes a model for the errors in best case. And then lastly, we want to infer the quantity like flow in our case, the V, and we do this by an inversion. So a bit similar to a matrix inversion. And there are several methods out there. The classical one is global modes, and the observable is like global mode frequencies or amplitude ratios between different modes. And the method, then there's the method from Greer et al. They use ring diagram analysis, where basically shifts in the frequencies by local flows are used to infer solar interior flows. And Hanasoga et al. Use time-distance Hilly seismology, where the travel time of waves in the solar interior are measured and then used to infer the flow. So how to estimate a spectrum in Hilly seismology? This maybe is not so much known to everyone, but first of all, one estimates what has the observable that one has, just as in the last slide, and then one produces an estimate of the flow. And this estimate of the flow always is some linear combination of the observable. And what I'm trying to show you here is basically how the estimate of the spectrum, which is a squared quantity, depends on the interior flows in the truth, because it will reveal something to us, something quite important. So if you plug into the estimate of the flows, basically the assumed reality, so some linear model dependence of the interior quantity, like the flow, and you take a square to get a spectrum, then what you're left with is that you have all combinations, and at the end, the expectation value of the flow at 2 different locations comes into play. So this is basically a correlation function of the flow at 2 different locations. And if you're lucky and you're in Cartesian geometry, you can get rid of the horizontal correlation by a Fourier transform, but still you're left with a correlation in vertical direction. So the vertical correlation of the flow, say whether it's correlated for 1 megameter or 10 megameters, which is unknown for the solar interior flows, this is already an input basically to the estimated spectrum. So the difficulty for estimating a spectrum is that this correlation function is not known for the true flows in the sun. So we can at best make an assumption, and then we're still left with this being unknown, unless we try to actually infer it at the same time. But until now, no one has done this yet. So basically, to illustrate this a bit, so the spectrum is sensitive to the interior spectrum and to the interior correlation function. And the sensitivity function basically is like something like a normal sensitivity function squared. And in this Cartesian case, you can basically only consider the vertical correlations. And this is how this sensitivity looks like. So basically, one is sensitive to the target depth, but one is also quite sensitive to the surface flows. And then the true spectrum that, or the spectrum that is estimated at the end, is a combination of this sensitivity function and the interior spectrum and correlation function. And if you take them, if I in this case took the Muram flows and multiplied, and this is what I obtained. So basically, this is how this shows spatially what depth contributes how much to the estimated spectrum. And you see that the estimated spectrum is mostly due to surface flows and not to flows at interior at 0.96, where it was targeted to be. Of course, this could be improved, and this should be improved, and other methods, for other methods, this might be different. But I'm just saying it would be good to, if one infers the spectrum, also to look at the spatial correlations of the flows and how they might, impact the result. And then third, young person at MPS looking at this convective conundrum from the spectral point of view was Bastian Poxorf. And in his PhD thesis, towards the end of his PhD thesis, he used actually the ring diagram pipeline and also local correlation technique, similar to the Rodier result. And the good news is that the results that he obtained were more or less consistent with some other observations. At least there were observations that were consistent. So first of all, his LCT results, they were more or less consistent with the Rodier results, which already is quite good. And they extend basically all the way down to L equals 1. Yes, and the ring diagram results from the ring diagram pipeline he obtained, especially the surface flows, also they were consistent with the LCT results that he obtained. But still there was some discrepancy with the Hanasoga results. But if you remember what I said, there's a factor of 4 in the energy from the correction I would apply from my analysis, then the curve from Hanasoga et al. Would move up by a factor of 4, and then it's nearly in the range of what Bastian found. So overall speaking, I think it's, at least in my opinion, it's fair to say that now we have a baseline for comparison. I think that the agreement between the ring pipeline and the LCT results from Bastian, together with the agreement of Bastian's results with the results of Rodier et al., I think this shows that indeed, at least the surface flows on the sun, they're weak at large scales and much weaker than the simulated ones. And I think these results can be used to compare to simulations. So I think I'm maybe going a bit long about this stuff and going to the observations so much, but I think it's important because there has been quite some debate. Is this even correct? Are the flows even so weak? Of course, in the deeper interior, like 0.96 and deeper, it's not sure yet whether we have reliable results or not. But at least for the surface, I think, or the near surface regions, I think it's fine to say there is a conundrum. Now, I'd like to go a bit more into ideas for explaining or solving the convective conundrum. And as I said before, this is to some degree likely related to why supergranules are there on the sun. Because the question, why the spectrum is low at large scales, it's a bit the same, but another question posed in a different way, like why is the supergranule peak so high? And I'm presenting a few ideas. I think from my point of view, I hope this fits more or less what the general idea is. And if you have a little bit different interpretation, just at the end we can discuss. It would be nice to do so. The first option, I think, is maybe also a bit obvious, but I'd still like to state it, is that most likely in due time, numerical simulations cannot attain the resolution which is needed to resolve all necessary scales until the viscous scale for performing true direct numerical simulations for a global solar model. So this means that the simulations that are there for the global sun are always large eddy simulations. They simulate the largest scales, but assume something about what's happening at smaller scales. This is just to keep in mind that always, if simulations go a next step into a new order of magnitude in resolution, it could be that something new happens. We don't know. But of course, we are all astrophysicists, so we would like to know what's happening in the sun without waiting forever. So let's see what people have proposed. So the second option then is, I think the first one that has been proposed, like a physical model, is the so-called entropy rain. And the main idea, I think, was from Sprott and then was taken up by others like Brandenburg and Anders et al. And the main idea is that large-scale convection in the global sun works like this. So at the surface, radiation makes an intense cooling of the plasma, and then there are small, cold, and heavy and fast downdrafts which develop. A little bit like in the study on the right-hand side. So when the stratification in the interior is large, so density grows fast, a thermal, so a blob which is colder in this case than the surrounding, it will sink, and while it sinks, it is condensed. It becomes smaller due to mass conservation, because the masses and pressure are much higher in the solar interior. And as it sinks, it's further condensed. It will speed up and basically tunnel through all the way until some depth, maybe the bottom of the convection zone, maybe half the convection zone, who knows. And at the same time, the upflows that will appear are just gentle. They are just very slow, gentle upflows, which don't have so much a big thermal contrast to the surrounding. So the consequence of this is that the cold downflows carry the major part of the solar luminosity. And for global simulation, these small and cold downflows might be so small that they are not resolved. And so this is a bit similar to assuming like an artificial flux, which is not resolved in the simulation, which was done by Lord et al. To model weak large-scale flows, or to just decrease the luminosity, as other simulations have done, basically to get a simulation result that looks closer to the sun. And there are consequences from this idea. The main consequence, I think, would be that the presence of these small downdrafts and at the same time large, very gentle upflows, it changes the mean stratification. This is because the downflows and upflows have different density, and basically denser material is transported downwards, and less dense material upwards. And since this is not at the same, not symmetric, this will change the density stratification. And the change in this density stratification, it will change the so-called superadiabaticity. So this is the degree of convective instability of the convection zone. In a typical stellar model, this is assumed from mixing length theory. But in compressible convection, like this example here, in the entropy rain idea, this will change basically the background stratification in such a way that the large scales are less buoyantly driven than they were without, or than they are in a standard solar model. So that at the end, the large scales produce only gentle upflows. And even it can become more extreme in the sense that even the bottom part of the convection zone is superadiabatic, so a stable layer may form. And this layer is quite weird because large-scale flows are stable in this layer, and only large-scale flows can develop because the scale height is very high. But the small-scale flows, they still come from the top and might penetrate through this layer. And this could be actually also in the bottom part of the convection zone, where no one knows how big this region would be. And by this effect, the large-scale flows are weakened. And in this picture, supergranulation would be like the largest buoyantly driven scale on the sun. And to relate this to observations, I have put a few ideas, namely that one idea is that, I think one way to relate it is that the the thermal contrast of supergranules is quite low. So if you look at the intensity maps of the solar surface, you don't see supergranules. You have to average over many supergranules to see the intensity variations, which are on average about 1 Kelvin across the scale, across one cell only. Of course, this doesn't say yet how much the temperature contrast is in the interior of the sun, but maybe it's a clue that tells us that supergranules are buoyant, but only weakly. And one would have to see how this is actually the case for the largest scales on the sun. And the second relation to observations is that inertial modes that were recently in the recent times discovered on the sun. So this could be Rossby waves or thermal Rossby waves like banana cells, or other modes that are have Coriolis force as a restoring force. Many of these modes are likely sensitive to this background superadiabaticity profile. So basically anything that convects or has a response to buoyancy force will be sensitive to the background superadiabaticity profile. I already looked at P modes and it looks like they're not sensitive enough so that one can infer this profile in the convection zone. Basically, it's about inferring the Brunt-Weisseler frequency. Yes. So the second idea that was suggested is the idea of suppression by rotation. The main idea basically is that if you have a simulation and you increase the rotation rate and you increase it ever more, then the large-scale convection are more and more suppressed. This is shown in the right-hand spot where spectra are plotted for different Rossby numbers. And basically to the bottom here, the rotation speed is increased until you at some stage, like the red curve, you have a spectrum that looks similar to the sun. And the conclusion from these studies is that the deep solar interior convection is likely in the low Rossby number regime. This means that rotation is strong and convection is dominated by Coriolis forces. So just to look at this a bit, I wrote here the definition of the Rossby number is basically the advection term in the Navier-Stokes equation divided by the Coriolis force. And you can also estimate the order of magnitude by taking a typical flow velocity and length scale and the rotation rate. And to relate this to observations for large-scale flows like equatorial Rossby waves, for example, I estimated the Rossby number is very low, 10 to the minus 3. Also, they have Coriolis force as restoring force, so Coriolis force should be important. It's one can expect this. And for supergranules, I estimated just with a length scale, I think of 30 megameters and flow of 200 meter per second. And then the Rossby number is about 2. And so the idea in this picture is that supergranulation is basically the largest scale that is not strongly affected by Coriolis force. And scales significantly larger than that are affected and suppressed. But I want to caution here that just the fact that solar flows have a low Rossby number does not imply directly that the rotational suppression caused the convective conundrum. Because it could be the other way around. It could be that the flows are suppressed in some different way, like the entropy Wren idea, for example, and then the Rossby number is low, and then maybe a little bit further suppressed by rotation. So the reason for the small Rossby number could be also that just the flows are suppressed by a different way. And another hint in connection to observation could be that Hanasoga et al. In 2021, they claim that the convective flows are stronger near the equator. One can't see, but I think there's one difficulty still with the methods that use mode coupling, like Hanasoga et al. And also Schad et al. For meridional circulation. This is because systematic effects of mode coupling have not really been understood, not really been studied. And it's known from basically all seismic methods that they are prone to systematic effects and they have to be understood. Okay, so the fourth idea that has been proposed is magnetic suppression. And the main idea is that magnetic fields at large scales are strong enough to suppress convective flows. And so in other words, that magnetic energy at large scales is of similar order of magnitude as kinetic energy. And to relate this to observations, I've done some estimates. So for supergranulation, for example, magnetic field, typical magnetic field is 5 Gauss. Found some number in network magnetic field. Velocity again of 200 meters per second, and then I get a ratio of 3000. So kinetic energy is much larger still than a magnetic energy, at least at the surface. Of course, in the interior, we don't know. So it might be different there. But at large scales, it could be actually could be the case, I think, because if you have a typical flow velocity of 1 meter per second, say for Rossby waves, it gives you a factor of 40,000 in the energy. And if deep fields are the same or stronger, then there at least magnetic fields might suppress large scale flows. And I have to say that there are more options, especially for the emergence of supergranulation. Many ideas have been proposed, and they are nicely summarized in the review by Rincon and Riotor. And one idea is also, another idea is like scale selection mechanisms. Also in Rayleigh-Bernard convection, they found these. I will not talk so much about it, but there might be different ways why this scale is selected. Another one could be that just the stratification, it selects this specific scale of supergranulation. And for the remainder of the talk, I'd like to go a little bit beyond spectra. So we have looked a lot about spectra. On spectra, I looked a little bit more and go beyond that. Why would I like to do that? I like to do this because spectra only incorporate partial information on the flow. So for example, here I have a flow field from the simulation of Lord et al. It's the vertical flow at some depth. Here it's shown 0.98 solar radii. And it looks like you would expect convection to look like. And what I did is I took just these flows and I just did a Fourier transform and multiplied it with random phases, basically. I just made the phases random, so I obtained this flow map now. Basically, these two images have the exactly same spectrum, but they look quite different. You can see immediately in the left-hand side, it looks like convection, the right, it doesn't. And so the thing is that there's potentially quite important information stored in these phases. And I was interested in these phases, and I would like to understand convection by using these phases. And not only that, I'd like to create like synthetic flow fields, also to test heat testing methods, but also to compare to simulations maybe. And I thought this could be an idea to characterize convection better. So after quite some brain work, I came up with a model and statistical method how to do this. And I'll guide you through what's happening here. So one of the two images here is the observations. The other one is the synthetic map I produced by this method. In the observation, we took correlation tracking velocities and computed the divergence, horizontal divergence of the flow. And this is what's plotted in these maps. So white spot is basically a outflow location, and a black spot is a converging inflow location. And in both maps, you can see there are things like an outflow location surrounded by a network of inflows, also here, which look like supergranular cells. And what I then did, I took the Fourier transform and I computed the triple correlation in Fourier space. So this is like a power spectrum where you take two correlation of two spectral quantities, but here I took 3. And then there are some identities that you don't. The third one, it is always have to depend on the first 2 ones, and so on. And this quantity is called the bispectrum, so next order spectrum, basically higher order correlation. And is also related to the skewness, which is a statistical quantity of the histogram. So the histogram of these divergences, it is not symmetric like a Gaussian, but it's skew. So it is shifted to a little bit to negative divergences. This is due to the difference between up and downflows and the difference between outflows, which are due to upflows, and due to the inflows, which are due to downflows, basically. And the model that I produced now is a model which has 2 components. One is basically Gaussian, it's somewhat a linear model, and then there's a nonlinear component. And the Gaussian linear model, basically, it just uses the power spectrum, the ordinary power spectrum of this of these images. And then I added this weak nonlinear component. It has about 5% of the power of this of the linear component, of the Gaussian component. And what I did is I used this bispectrum here, and as a coupling coefficient to couple basically two wave numbers. And I didn't do this for fun, but I did this because literature told me this is how to reproduce data set that has not exactly the same, but a very, very similar bispectrum, so second order spectrum. And the data set that I generated with this model is one of the two. The other one is the real one. And until the end of the talk, you can try to guess which one's which. So this is a statistical model. One could say it's only a statistical model because it's not a hydrodynamic one. But still, I think it's interesting because it's the first model to reproduce the shape of solar supergranulation. So I'm a bit happy about this, although it's not so physical, but anyway. And but still, one could try to think whether this result could be interpreted physically in some way. It's not so easy, but I'm working on it. So let's try. One way to interpret it is the following way. So not only can we use this method to generate the flow, this synthetic map, but what can also be done is basically I can try to make an estimate of the nonlinear component. So one of the two, again, is the data, and the other one is the synthetic one. And I can just, instead of generating the nonlinear component like this, I can just use the observations to estimate it from the observations, because anyway, the component is small and the major contribution will be from the Gaussian component. And what one finds here is that, so red means basically positive values and blue means negative values. What one finds is whenever there's a nice thing that looks like a granule, like this thing, for example, then the nonlinear component, it amplifies the structure. Like the outflow locations are made stronger, and the network locations, kind of like a ring of inflows, it is also made stronger. Also, it's visible here, for example. Yeah, this one's not so nice. Down here, maybe. Yeah. Yes. So basically, what one can learn from this is that these higher order correlations, they might help to constrain how buoyancy is acting on supergranular scales, because it basically would say here's an outflow, buoyancy is going upward, and here's an inflow, downflow, buoyancy is working downwards. This is important because the intensity maps, it's hard to use them for constraining buoyancy, because usually you would expect buoyant upflow is hot, intensity is large. But that's not always the case, and often not for supergranules, because this is because of the network magnetic field. It's the effect of magnetic field via bright points and other features on the intensity maps is such that the inflows, at least the magnetic locations and inflows, are on average brighter than the outflows of supergranules, which are non-magnetic usually. So one has to in a complicated way see what the magnetic field is doing, and this way it would be possible to constrain the buoyancy. And also, it's this quantity, this bispectrum, is related to some turbulence quantities. For those who know, it's related to the spectral transfer of kinetic energy from scale to scale. Okay, to summarize. So I think first we have an observational basis for the convective conundrum, at least close to the surface. So solar large-scale flows have a small amplitude, and this is likely related to the emergence of supergranulation. And small is always understood here in comparison with simulations, and smaller than the supergranular peak. And there are several ideas that have been proposed for explaining the observations, which are all more or less, at least in some way, consistent with observations. So there's entropy rain, there could be rotational and magnetic suppression, and potentially there are more even ideas. And finally, higher order statistics may help to better constrain the convective conundrum and the emergence of supergranulation. Thanks for your attention.
Thank you. There is I see already some discussion in the chats already. Lauren, do you still want to ask a question, or you feel the question is already answered, but well answered in chats?
Yeah, mine, well, no, I think it basically already answered. I was wondering about granulation. I mean, we do understand the length scale of granulation. I think the answer is yes, we do.
Granulation, yes, yeah. But supergranulation, I think no. You were asking about granulation or about supergranulation?
Yeah, sorry, I had a question in the chat. Do we understand the length scale and time scale of granulation?
I think so.
Directly. I mean, is that kind of well understood?
I think so. The review of is it Stein and Norton,
Right,
maybe
okay.
living
Yeah.
review in solar physics. I think everything is there.
Yeah.
I think it's the scale height at the surface together with the radiative transfer. Yeah. Yeah, this is the same argument is taken by some people to say, okay, if it's the scale height that dictates the scale, then it could be the supergranulation is saying it's made at a depth of 30 megameters, or where the scale height is 30 megameters, and below that there's really no convective forcing. Yeah, some people think this, but
Okay, there are two people raising hands. Irina first, and then Gustavo. Irina?
I believe Gustavo was first.
Oh, I'm sorry. I'm sorry. I saw you first. Sorry.
Go ahead, Irina, please.
I have maybe too many. First, about origin of supergranulation, I would like to say it is not still under discussion. So it's, I have several points actually. I will give two and continue after everybody. So first question regarding your slide when you compare results with Hanasogi with Muram simulations. What I'm a bit confused. Maybe you mentioned this. You have spherical degree, very low spherical degree, well below 100. But Muram simulations are local simulations, and I don't see any way how you can compare global scales from local simulations.
yes,
Can you
that's a very
comment
good
on this?
question. So this is a special Muram simulation. So that's the work of Lord et al. Yes, or the thesis of Jesse Lord in 2014, and he made basically large box simulations with Muram. So they are 200 megameter times 200 megameter in horizontal extent, and I think 50 megameter deep. And
I'm sorry, I just check it. I just check it. Even
no
200 megameters, it is still not enough to have 20 harmonic degrees, right?
Yes, yeah, this is what you get. So basically, 2 pi, no, pi times, what is it? Pi times solar radius divided by 20 gives you 200 or something like that. 2 pi times solar radius divided by 20 is 200. Yeah, this is how you compute this.
I don't know.
Okay, yeah, of course. I mean, this is
your work, but
of course I understand what you could say that in the Muram simulation, a scale at this size is likely not well modeled. This could be true. Yeah. But you know, one could also think about this study, assuming the flow is not from Muram but from somewhere else. It's just some synthetic flow, which could be a flow for the sun, a convective flow. And for this flow, then you could do this exercise, say, for any flow field, and then see whether the method works. But what is interesting about the Muram simulation that also it shows this simulation was compared to results from local correlation tracking from the sun and performed on the images from the simulation. And also that was found that the large scales were larger compared to the sun in a similar way as global simulations have larger amplitude at small scales. So at least the amplitude of flows in the simulation at large scales, it is similar to other simulations.
Okay. And second, it just a comment when you discuss about local simulations. You discussed about discrepancies between observed kinetic energy spectra and simulations. It is, I think, main problem is not just special resolution of simulations, any kind. I don't want stress on local, on global, but also it question model setup itself. For instance, say if I include more magnetic flux in my model, I can get one spectra, and if it will be near hydrodynamic case, it will be say maximum value for energy will be much higher. So, and I think it is an extremely difficult question, and even decide what reason of such discrepancies, it is also a big question itself. Yeah. Thank you.
Yeah, I agree that there's some freedom in the simulations, how they are set up. But I also think that, you know, if one has many observations to compare the simulations to, like you have the spectrum, you have the shape of supergranules, and other features, maybe larger scales like Rossby waves or some intermediate scale features, whatever. And if you compare observations and simulations on different features like this and the higher order statistics that I proposed, and if you some simulation successes in matching all of these, then it's probably hard to make another simulation that also does so, which has a different setup. Like, at least it's a guess.
Gustavo and then Phil.
Hi, Vincent. Thank you for the talk. Very nice.
Thanks.
I have perhaps a different interpretation of what the convective conundrum is.
Yeah.
No, not necessarily the comparison of the simulation with the simulations of the observations with the simulations, because simulations, we know that they have issues in reproducing this solar differential rotation of these kind of things. But my understanding is that the conundrum is between this black line that you see from Greer et al. In 2015 and Hanasoge 2012. So that's a huge difference between these two results. And of course, simulations are not or have to reproduce something of this very low energy that Hanasoge found, but you need to have in mind that the global simulation, they don't reach all the way to the surface. They normally get up to 0.96, and all of these, or as you say, the more reliable results are the ones at 0.99 or even higher. So there is no very direct way of comparing these results with the global simulations. Of course, they are a fantastic tool. I do this kind of simulations, but to me, and the other thing is that, of course, the simulations work as if convection were driven by buoyancy, by a buoyancy force. And I incline to believe that the entropy rain is possibly happening. But in this sense, it's not necessarily the difference between the simulations and the observations, but more the difference between different observations and also the difference of these observations with the mixing length theory. So yes, that's my understanding. Because global simulation, they don't get, they are full of artifacts and tricks to get what we want to get, which is the solar differential rotation and maybe circulation and this kind of thing. I have two more points that more questions. Maybe I do my question first and then you answer, or do you prefer to?
Yeah. Well, should I comment on your comment, or do you want to ask another question?
I don't know what you prefer.
You can ask.
Okay, the other thing is I found quite interesting that it was you that compute this ratio between kinetic and magnetic energy, which is about of the order of 3,000.
Yeah.
So I would like you to comment a bit more on that, because this kinds of contradicts the results of Jota in this paper of 2022.
Well, yeah, okay. So I here, this I should have said better, yeah. So but the numbers I compute here are for observations of supergranulation. So they have a typical flow velocity of 200 meters per second. Average supergranulation maybe 300 also. And if you look at observations of network field, it's I think 5 Gauss, not so bad value. Maybe someone else knows more, but I looked at some papers and this was more or less what they stated also on observations of supergranules. So I then computed using a density a little bit inside the sun, like at 1 megameter depth or something. Yeah, of course, one could go and take a surface density, but it's maybe not a factor of 1,000.
Right. So
maybe
this
it's 10 or 100. So yeah, of course, this number is a bit, yeah, who knows how to compute this really. You have to put the density in here for the kinetic energy. Yeah.
So, but if you go down, then the density increases. So perhaps this radio continues being larger than 1.
I know I used from, I think it was more or less 1 megameter or something depth. But still, it's the difference in the surface. So
yeah, no, but it's
I can look it up at the differences.
It's quite a huge number. What he claims that is solving the convective conundrum is a small scale magnetism that is stronger than, or that has more energy. It's a super equipartition. So at the larger scales, I agree, it could be a large scale magnetic field could still help to solve the convective conundrum, but we don't really know for sure.
Yeah, so this I did just before the talk this morning with my calculator. So of course one can take this and make a real study out of it.
Right.
Compute these numbers really with data and so on, and look and so on. This would be a comparison of the work of Jota to observations, basically. And I mean, he in his work shows that in the case where he simulates with very fine resolution, there the kinetic and magnetic energy, which are the green 2 lines here, they are close to each other at large scales, while they're not at the other resolutions.
Yeah. And finally, you created this synthetic data for supergranulation. What is exactly the difference of your method with the method of David Hathaway? Because he creates some synthetic supergranulation in the spectral space.
You mean the photospheric spectrum that he generates?
Yeah.
Yeah, I think if I understand correctly, what he's doing, basically he goes back and forth and changes the phases. So basically he takes the power spectrum, and then I don't understand really how the method works, what he's really doing, but I understood that he takes the spectrum, generates some phases, and then changes the phases until it looks like the sun. But it looked like when I read it, it sounded to me like a black box. So if someone knows more,
I don't know if Lisa is in the audience. No, he's not. Okay. Yeah, thank you, Vincent.
Yeah.
I don't know if you want to comment about the convective conundrum.
Thank you. Yeah, I think the other comments that you made, I'm more or less of your opinion, I think. Just that, I mean, I think the simulations should be better than mixing length theory. So, and the difference between Greer and Hanasoge. So this is a little bit the point I wanted to make in the slide here. So before there were just two observations. There was Greer and there was Hanasoge, and that was it. So basically, one wouldn't know where one was at. And now there are the ring diagram results from Bastian Proxorf, and LCT results, which in between the two but at least which say stuff's getting weaker towards large scales.
Right. Do you know why these results have not been published in any journal already?
They're in his PhD thesis, so there's what it is. You can cite it. And also, it has a proper DOI. You can search for it. It has a proper DOI, and it was published in the University of Göttingen. Yeah, I think they wanted to submit a paper, but it hasn't happened.
Okay. Thank you.
You're welcome.
Phil also have a question, and Nick also mentioned mentioned something in the chat. We shall let Phil.
I know I can see the chat. I found the chat.
Phil, do you want to ask question first?
Yeah, I look at it from the observer's perspective and assume that the simulations are trying to show something mimic the observations. There's some observational constraints that tend to not get mentioned very much. If you look at Tom Duvall's movie of divergence from time-distance seismology, you see that, and then superimpose on that magnetic fields. And you see the magnetic fields just sort of move through the supergranules. They slide around the edges, in a sense. So the supergranules are rotating slower than the magnetic field patterns. So magnetic field patterns are believed to be rooted deeper. And supergranules maybe just the fluff on top that is just being pushed around by the fields. So it's likely that the fields are somehow correlated to the scale of the supergranules, it would seem. I think your estimate of the strength of the fields is really an underestimate, because the fields are almost always unresolved as measured. So it's net flux over a big area, and they're actually more compact. They're tens of kilometers, not hundreds of kilometers. So DKIS will probably make some of those better, because the data from the Swedish telescope is showing that little tiny points in just granules is where the fields are. So it's probably an underestimate. The other thing is that we see is that supergranules last about a day, and there's a preference for the next supergranule in the vicinity to rise up on the leading edge of the previous one that failed. So there's also a correlation there in time with location. So both those things, I think, should somehow be something to work toward in the simulations.
Yeah. Yes, thank you for the point with the magnetic field. I think this is, and for DKIS, I think this is very interesting if someone makes observation. And concerning the appearance of the next supergranule at the edge of the old one, I think this is related to the wave-like properties, right? So this is related to this, I think, which also, in simulations, I don't know, no one is commenting on it. But I think it's interesting what you mentioned. First, what was Tom Duvall's, did you understand correctly, movies of magnetic field simultaneous with divergence?
Yeah, he made movies of divergence at the center of the disk, time distance, and then superimposed high resolution magnetograms.
Yeah, and they move across the supergranule.
They move around them.
Ah, yeah. Okay. I thought that there's a study by Langfeld et al. He tried to use like Cox simulation to reproduce the magnetic field, but only the magnetic field strength, I think, not its exact movement or features.
Yeah, Tom's here if you wanted to comment on this.
Tom?
Okay. Yeah. So what was done there was F-mode time distance helioseismology, looking at the divergence, and with the observed magnetic field at the surface. And we made movie of that. I think that was when Laurent was a student, and we worked on that together. And so I think the speed of flow of the features and the divergence features is not the same as the magnetic features, and so leads to this look that magnetic seems to move through the divergence maps. This is what you're talking about, right, Phil?
Yes.
So what do you think is the magnetic field doing, Tom?
What do I think it's doing? Is that?
Yeah.
Well, I think it doesn't move through the supergranule, but around the edges of it. And why is this? I don't know.
Okay, interesting.
Let's sort of, oh, sorry, I don't mean to have this.
Sort of a bigger scale. Yeah.
But yeah, so that was sort of what was crossing my mind, Tom, a little bit. Is it, taking Vincent's physical interpretation of like that this being buoyancy related. So far, at least to my knowledge, we've sort of interpreted magnetic features gathering around supergranular, edges being an aspect of the downflows, but the buoyancy aspect of it might, that would have implications there. So that, if it has to do with buoyancy and the magnetic field being driven to those edges instead, yeah, I don't know. I don't have a fully formed thought about that, but that was what was sort of going through my head in terms of, you're finding that the magnetic fields that kind of stick to the edges of the supergranulation.
You're saying that, the magnetic field, I think, sticks to the edges because there's convergent flow. And so this amplifies carries the magnetic field and amplifies it. But of course, also the converging means downflow. So why the magnetic field is not carried away?
Right.
It's just the effect on there's a convergence and then you have amplification, I guess.
Right. I think that's been the interpretation so far. But I think adding buoyancy into that conversation would be interesting and maybe tie
you would. You would have a downflow, a cold downflow, which is buoyantly sinking. Because it's, not buoyancy is not upwards, but downwards directed in this location. So you would have buoyancy force going downward, but magnetic field, what would it do if it's collected? Maybe it's just pushing up or something. It could be. Who knows?
Okay. Nick has asked a question in the chat, but he had to left early. He already left. He's let me just repeat his question. If you want to say something or you want to reach him. So he asked he would like to discuss with people, is entropy rain really different from any other sort of convection? What is the different physical process?
Yes, it's also convection. Yes, is it different? No.
It is.
It is. I would say it's not, and it's just a different. It's a specific mode of convection, I would say.
It's also convection, but it's non-local. Mixing rain is local.
Yeah, so entropy rain is non-local. It's very non-local, in the sense that only a specific location thermal will start to go, and it goes all the way through the convection zone. And mixed length theory just means that only at one scale height it will move, and next scale height it's something else will happen, right? But Of course, mixing links is not the whole truth about convection, most likely. So I would say it's used as a term because the way if this is how convection goes in runs in the sun, it's much different than it was previously thought. That's why it has a specific name.
Okay, I think that's the last question. Irina, you still have the hands raised. Do you still have question,
Yes.
or is the old one?
Yeah,
Oh, okay. Please ask.
yes.
Please ask.
My question is about Rossby number. And when we discuss about different way, you discussed about what Rossby number should significantly decrease in deeper layers. But as you know, we have subsurface flows already measured, they are available. Have you tried to estimate Rossby number?
Where? Estimating Rossby number where?
In interior, in solar interior.
Not using observations, no.
No, I mean with observations, because
No. I mean, which
have
observations would you
just
take? The one from Hanasoga et al., the one here,
no,
the one up there, or which one?
It can be observations. I don't know, from global hydrosmology, from just subsurface flow maps. I don't know. It can be. I believe subsurface flows are available through HMI pipeline. At least, no, of course, not very deep, but still available. I just curious if.
I think no real study has been done to directly estimate the Rossby number. You could take if spectra have been produced, one could use that, or if I don't know. I don't think there are not many studies which publish flow maps of the interior from convection. It's not so easy to detect individual flows, because for spectra you can average statistically, but for individual flows it's difficult. You have just one realization.
I remember I have seen some papers with attempts to estimate Rossby number below surface. I don't remember, unfortunately, just a point. But in any way, it will be interesting to see if different groups will try to compute it and how they will, I don't know, agree or disagree. Even disagreement always even more interesting, actually.
Paul Roger Guru, he's saying, I should say the answer to the question, which models which.
Yeah, I want to ask about that as well.
Okay, so let me see. Yeah, I think the right one is the real. Let's see. Here we go. Yes, this one actually is easier. This estimate here, because the right one, it is not periodic, and the left one, it's periodic. Yeah.
Okay.
Yeah,
Thanks. That's what I thought. Yeah.
And there was one more question I read from Shear. Have the observations only been done with ring diagrams? No, I think the curve from Greer et al., it's from a ring diagram, and Hanasoga, the bottom curve, is from time distance. And the intermediate curves from Bastian Poxhoff are from ring diagrams and from LCT. But I don't know whether he used P modes or F modes, but he certainly has written it in his thesis. I think there should be P modes because there are some depths which go deeper, like 0.97.
Okay, I think that's all the questions. Thanks to Vincent for the very nice talk, and especially for the very long and detailed discussion. Yeah, it's a great chance to ask so many questions and have them discussed here. Oh, Jason, sorry, Jason, you raised hand. You have.
No, I was looking for a clap button, but it's,
okay.
it's not there.
I was like,
yeah, it was nice to see you. And
okay.
All the best for your project. It looks quite different. It looks quite interesting to see how many people collaborate.
Yeah.
Thank
Let's
you.
see, now for this, I have to look at the planets now.
Yeah.
Yeah, why
If
not?
ti-
Yeah,
Yeah,
let's
if
see.
time allows, you're welcome to join more
Yeah.
COFFIES events.
Thank you.
Thank you.
Thank you
Goodbye.
very much. Very interesting.
Thank
Thank
you.
you. Thank you. Bye.
Bye,
Bye-bye.
thank you.
Bye.
Bye.